So welcome back. Now in this lecture I am going to discuss the system of linear equations, and I will try to solve the system of linear equation with the help of the direct methods and indirect methods. So for the direct methods we have the matrix inversion method, Cramer rule, and then I will not discuss these two methods because you already know these two methods. Now in this lecture I will discuss the Gauss elimination method and Gauss-Jordan method. Now before that I will discuss the pivoting, and here I will discuss the partial pivoting and the complete pivoting, and I will discuss what is the importance of this pivoting in solving a system of linear equations. So let us discuss the solution of this system of linear equations. So solution of system of linear equations. So consider a11x1, a12x2, then say a1n(xn) equal to say b1, then we have a21x1, a22x2, then a2n(xn) say equal to b2, then we have a31x1, a32x2, then we have a3n(xn) equal to b3, then say the nth row is your am1x1, am2x2, then we will have amn(xn) equal to bn. So we have this system of non-homogeneous system of equations. Now in the matrix form it can be written as your a into x equal to b, where your a is the coefficient matrix, which is your a11, a12, a1n, then we have a21, a22, a2n, then the nth row will be am1, am2, then we have amn, and your x will be equal to x1, x2, then we have xn, and your b is equal to b1, b2, then we have bn. Okay, so here we will have bm, and this is your bm. Okay, now this system of linear equation has the solution of the form ax equal to b. Now the solution of this system of equation with the help of the matrix method is equal to x equal to a inverse b, provided that the matrix is non-singular. If the matrix is non-singular, then with the help of this equation we have the solution. We can also solve it by using the Cramer rule. Now here I am going to solve these equations with the help of the direct methods, and for the direct methods we have our Gaussian elimination method, then we have Gauss-Jordan method, and then the decomposition method. And for the indirect methods we have the iterative method, there are Jacobian method of iteration, and we have Gauss serial method of iteration. So let us discuss the Gaussian elimination method. Also your augmented matrix is given by your augmented matrix will be your A, the combination of A and B will give you the augmented matrix. So now our first method is Gaussian elimination method. Okay, now in Gaussian elimination method we will try to remove this augmented matrix in upper triangular matrix, that is in row reduced echelon form. Now we will do it with the help of the pivoting. So here we will reduce our augmented matrix AB in upper triangular matrix and then using back substitution we solve AX, we get the solution using the condition AX equal to B. So in Gaussian elimination method we will try to remove this augmented matrix in upper triangular matrix, and then using the back substitution we get the solution of this system of linear equation AX equal to B. Now here we will reduce this matrix in upper triangular matrix with the help of the pivoting. So let us discuss this pivoting. So first we have the partial pivoting. Now what is the need of this pivoting? So in order to improve the numerical stability of an algorithm, we use this partial or complete pivoting. Now the partial pivoting reduces the round of error. So that is why we are using the partial pivoting. Here I will solve a problem with the help of the pivoting, that is with the help of the partial pivoting and complete pivoting, and again I will solve the same problem with the help of without any pivoting. So in partial pivoting, so here we will follow the following steps. First we will find the numerically largest value in a column. Say this is your first column, and here in this first column we will try to find out the numerically largest value. Now if it is A11, suppose that A11 is numerically largest value, then we will annihilate, that means we will reduce the remaining elements of the first column to 0. Now in first step, first of all we will find out the numerically largest value. Now with the help of this numerically largest value we will try to reduce the remaining elements of the first column to 0. Now in second step, say this is your, say in the first step, say this is your pivot element, that is, suppose that this is the numerically largest value. Now with the help of this element we will try to make these elements 0. So after first step of iteration, after first step of computation, these all elements are equal to 0. Now in the second step, say this is your pivot element. Now with the help of this element we will try to remove the remaining elements to 0. So continuing this process, finally we will get a upper triangular matrix. Now with the help of this upper triangular matrix we will use this condition, and then finally we will get the values of xi. So in this case, in partial pivoting we choose numerically largest value in a column. So if it is at the first column, say if it is at the, say this, if this numerical value is at this place, then with the help of this value we will try to annihilate the remaining elements. Now if it is not the numerically largest value, suppose that this A21 is the numerically largest value, then what we will do? We will try to interchange our rows. So in the second step, or in this, if this is the numerically largest value, then with the help of this one we will annihilate the elements. If it is not the numerically largest value, interchange the rows to get the numerically largest to get the numerically largest value. So interchange the rows to get the numerically largest value. Now here please note that we will change our rows only. So interchange the rows to get the numerically largest value. Only exchange of row is allowed. So usually partial pivoting is sufficient, but in some questions we will see that this is not sufficient. That means in that case we will need the complete pivoting. Now what is the complete pivoting? Again, to achieve the numerical stability of an algorithm, we will choose this complete pivoting. So in complete pivoting, again we will choose the numerically largest value. Now here in partial pivoting we have chosen the numerically largest value in a column, but in case of complete pivoting we will choose the numerically largest value in the submatrix A comma B. So choose the numerically largest value in submatrix A comma B. So here we will choose the numerically largest value in the submatrix A comma B. So this is our first step. Then now here we have interchanged our rows. Now in this complete pivoting we will change. Now to get the numerically largest value at this step we will change our both rows and column. Now to achieve or to get this numerically largest value we can interchange our rows and column. Again interchange rows and columns to get this numerically largest value. But note that while you change the column, your xi will also get changed. Suppose that if you change this x1 and x3, say here we have the n variables, say if you change this x1 and xn, then the values of the variable xi will get changed. So that means we will have to change our x1 and xn. So in this process, change. Now in this process we will change the order of xi. So after getting the solution we will change the order of xi as we have changed our columns here. Here we have changed our rows only, but here we are changing our rows and columns. So finally when we get the solution, then we will have to change the variables xi. Now let us solve a question with the help of this partial pivoting and the complete pivoting, and then I will show that why this complete pivoting is necessary. So let us start with the problem. So the need of this pivoting is to reduce the round of error. So here we have the question: solve x1 minus y1 plus z x1 minus x2 plus x3 equal to 2 minus 6 times x1 plus x2 minus x3 equal to 3. Then we have 3x1 plus say x2 plus x3 equal to 4 using Gaussian Elimination Method. Here we have to solve this problem using the Gaussian Elimination Method. So here we will solve this question with the help of, first without pivoting, then we will solve this question with the help of the partial pivoting. So solution without any pivoting. So the system of equation can be written as Ax equal to B, where your A is the coefficient matrix, X is the column matrix x1, x2, x3, and your B is the right hand side column matrix 2, 3, 4. Your augmented matrix is A comma B. So this is your 1 minus 1 1, then we have minus 6 1 minus 1, then we have 3 1 1, and then in the right hand side we have 2 3 4. Okay, now here I am not using any pivoting, so just reduce these two elements 0 with the help of this row R1. So with the help of this R1, say let us now R2 plus 6 times of R1 and R3 minus 3 times of R1 implies that now this R1 is fixed, so we have this. Then now from R2, in R2 we are adding 6 times of R1, so this is your 0. Now 1 minus 6 will give you minus 5, minus 1 plus 6 will give you plus 5. Now this 3 plus this 12 will give you 15, and now this is your 0. Again 1 plus 3 will give you 4. Here we will have 1 minus 3, so this 1 minus 3 will give you minus 2. Now here we will have 4 minus 6, so this will be your minus 2. Okay, so this is your augmented matrix after one time of these row operation. Now again, let us multiply this R3 by 5, then minus 4 times of R2 will give you plus 4 times of R2 will imply 1 minus 1 1 2, then we have 0 minus 5 5 and 15, then we will have 0 0. But now 5 times of this element will be minus 10, then plus 20 will give you plus 10, so this is your plus 10. Then we have 5 times of R3, so this is your minus 10, and here this we will have plus 60, so that means this is your 50. So now this is in upper triangular form, so your solution is given by Ax equal to B. So we have 1 minus 1 1, 0 minus 5 5, 0 0 10. Then for x we have x1, x2, x3, and for b we have this right hand side which is your 2, 15, 50. Now with the help of the back substitution, the first row is 2, the second row will be minus 5x2 plus 5x3 equal to 15, then we have 10x3 equal to 50. Okay, now from here we have x3 equal to 5. Now with the help of the back substitution, put the value of x3 5 here, so this will be your 25, then we have 15 minus 25, so minus 10, so our x2 is plus 2, and put the value of x2 and x3 here, so we have minus 2 plus 5, so we have plus 3, so our x1 is minus 1. So this is your answer of this particular problem without any pivoting. Now we will discuss the partial pivoting. Now solution with the help of the partial pivoting. So solution with partial pivoting. Okay. Please note that here your augmented matrix is A comma B is equal to 1 minus 1, then we have plus 1, this is your 2, we have minus 6, 1 minus 1, then we have 3, 1, 1, then we have 2, 3, 4. Here you can see that our numerically largest value is this minus 6. So we will try to set this element at this place. So for that, let us interchange our R1 and R2. So here we have the numerically largest value minus 6. So let us interchange our R1 and R2. So our R1 interchange R2 gives you, now this will be minus 6, 1, minus 6, 1, minus 1, then we have 3, now this will be a 1, then we have minus 1, 1, 2, then we have 3, 1, 1, and then finally 4. Now you can see that this is your numerically largest value, and this is your pivot element, and this is your pivotal row. Now with the help of this minus 6, we will annihilate these two elements. So that means we will try to make this 1 equal to 0, and then again we will try to make this 3 0 with the help of this minus 6. So for that we will use the operation. Now R2, in R2 we will use the operation R2 plus 1 by 6 of R1. Now here we will use the operation R2 plus 1 by 6 of R1, so this will become 0. Again in R3 we will use the operation R3 plus, now this is your 3, so we will use 1 by 2 of R1. So now you can see that here we have minus 6, 1, minus 1, then we have 3. This is your first step of pivoting. So now this element will become 0 because this is your 1 minus 1, so this is your 0. Then we have 3 plus 1 by 2 of this minus 6, so this is again minus 3, so we have 0. Now here we will have minus 1 plus 1 by 6, so minus 1 plus 1 by 6 will give you minus 5 by 6, so this is your minus 5 by 6. Here we will have 1 minus 1 by 6, so 1 minus 1 by 6 will give you plus 5 by 6. Here we will have 2 plus, say here we have this 2 plus 3 by 6, so we have 5 by 2. Now at here this is your 0, then we will have 1 plus this half, so 1 plus half will give you 3 by 2, then we will have 1, then this is your minus half, so this is again half, then we will have 4 plus 3 by 2, so this is your 11 by 2. Okay, so after one step we have these elements. Now you can see that here we have to make this element 0, and you can see that our numerically largest value is this one. This 3 by 2 is the numerically largest value in this column. So we will interchange our R3 and R2. So after interchanging R3 and R2, this 3 by 2 will come here. So this is equivalent to, so your R3, if you interchange this R3 and R2, we will get minus 6, minus 1, then we have 3. So here we will have 0, then we will have 3 by 2, then we have half, then ln by 2, then we will have 0, minus 5 by 6, then we have plus 5 by 6, then again we have 5 by 2. Okay, now this is your 3 by 2, and here we have minus 5 by 6. Now with the help of this 3 by 2, we will try to make this element equal to 0. Now what is your multiplier? Now this is your pivot element and this is your pivotal row. Now with the help of this element we will try to make this element 0. That means minus 5 by 6 plus x into this 3 by 2 has to be 0. So let us find out the value of this multiplier x. So you can see that this is minus 5 by 6 equal to minus x into 3 by 2. Now this will be equal to, so this is your 3. So your x will be 5 upon 9. Now when we multiply this equation by 5 upon 9, then you can see that this is your 5 upon 6. And then we will add this R3 in R2. So now using the operation, R3 plus 5 by 9 of R2, we will get, here we have 3 by 2, then we have half, then 11 by 2. Now this will become your 0. Because your minus 5 by 6 plus 5 by 9 of this one will give you plus 5 by 6. So this is your 0. Now again, here our 5 by 6 plus 5 by 9 of this element will give you, now this is your 5 by 6 plus 5 by 18. So this is your 20 upon 18. So we have 9. 20 upon 18, that means we have 10 upon 9. So this is your 10 upon 9. Now here this element will be 5 by 2 plus 55 upon 18. So this is your 18. Now this will be your 45 plus 55. So this is your 100 upon 18. So this is your 50 upon 9. So this is your 50 upon 9. Now with the help of the partial pivoting, again we have reduced this matrix in our upper triangular matrix. So our solution is given by Ax equal to b. So your A is equal to minus 6, minus 1, minus 1. Our x is 0, 3 by 2, half. Then we have 0, 0, 10 by 9. Your x is x1, x2, x3, and we have this b. Okay, now you can see that your 10 upon 9 into x3 equal to 50 upon 9. So we have x3 equal to 5. Now with the help of the back substitution, put the value of, now the second row will be, now we have the rows minus 6x1 minus x2 minus x3 equal to 3. Then we have the row 3 upon 2 x2 plus x3 upon 2 equal to ln upon 2. Now just put the value of this x2 here. So you can see that this is your 5 by 2. This ln by 2 minus 5 by 2 will be your 6 by 2. So this is your 3. So you can see that your x2 is equal to 2. And put the value of x2 here. So we have minus 6x1 minus 2 minus 5 equal to 3. So this is your plus 7. Here we have some mistake. Please note that this element was plus 1. So this is your plus 1. Again this has to be plus 1 and this is your plus 1. So here we will have plus x2. Now if you put the value of x2 here, so this is your plus 2. Now you can see that this is your minus 3. So this will go in the right hand side. So your x1 is minus 1. So let us solve another question with the help of this complete pivoting. So let us solve the problem 2x1 plus 4x2 plus x3 equal to 13. Then we have x1 plus 2x2 plus 3x3 equal to 14. Then 3x1 plus x2 plus 5x3 equal to 20. So let us solve this problem with the help of the Gaussian elimination method. Now here we will use the full pivoting. We will solve this question with the help of the full pivoting. So our augmented matrix is So in this case your coefficient matrix is 2, 4, 1, then we have 1, 2, 3, then 3, 1, 1, 3, 1, 5, and on the right hand side we have 3, 14, 20. So guess the numerically largest value. Here you can see that the numerically largest value in this submatrix is your 5. Please note that here I am using the full pivoting. So for full pivoting we will find out the numerically largest value in the whole matrix, in the whole submatrix A. So in this submatrix A, your numerically largest value is this 5. Now we will try to bring this 5 at this position. So for that, first we will interchange our R1 and R3. After that, we will interchange our C1 and C3. So while you interchange our C1 and C3, please note that in our solution, we will have to interchange our solution x1 and x3. Only in that case, this system of equation will get satisfied. So let us interchange our R1 and R3. So this is your 2, now this will be your 3, 1, 5, then we have 1, 2, 3, then this is your 2, 4, 1. Now we have interchanged our R1 and R3, so this is your 20, 14 and 13. Now our largest element is at the position C3, this is your A13. Now let us bring this element at this position. So we will interchange our column 1 and 3. So let us interchange C1 and C3. So you can see that this is your 5, 3, 1, then we have 1, 2, 4, then we have 3, 1, 2. In the right hand side we have 20, 14 and then 13. Okay. Now you can see that this is your numerically largest value. So this is your pivot element and this is your pivotal row. Now with the help of this element, we will try to reduce these two elements. So for that, we will use the operation. Now we will use the operation R3 minus 1 by 5 of R1. In R2, we will use the operation minus 3 upon 5 of R1. Now after applying these two operations, we have the values as the first element is 5, 1, 3, 20. Now here we will have 0, then we will have 1.4. Now here we will have minus 0.8, and here we will have the value 2. Here we have 0, then we have 3.8, then we have the 1.4, and then we have 9. Again, note that our numerically largest value is this 3.8. So we will try to interchange this R2 and R3. So just interchange R2 and R3, then you can see that this is your 5, 1, 3, then we have 20, then we have, now as we have to interchange this R2 and R3, so this will be 3.8, 1.4, then we have 0, 1.4 minus 0.8, now this is your 9, and then we have 2. Now this is your numerically largest value. Now with the help of this element, so this is our pivot element. Now with the help of this element, we will try to reduce this element 0. So let us take the operation R3 minus 1.4 upon 3.8 of R2. So this will give you 5, 1, 3, then we have 20. Now this is your 0, 3.8, then we have 1.4, and then we have 9. Now this will be your 0, and again this will become 0. Now minus 0.8, then minus of this 1.4 upon 3.8 will give you minus 25 upon 90. Then again in the right hand side we will have minus 25 upon 90. So now you can see that this is in upper triangular form. So solution is given by Ax equal to b, So your A is 5, 1, 3, 0, 3.8, 1.4. Then we have 0, 0, minus 25 upon 9. Then we have x1, x2, x3. Now in the right hand side we have this 20 and 9 minus 25 upon 19. So you can see that from here we will have the equation 5x1 plus x2 plus 3x3 equal to 20. Then we will have 3.8 x2 plus 1.4 x3 equal to 9. And then finally we have minus 25 upon 9 x3 equal to minus 25 upon 9. So our x3 is equal to 1. Now just put this x3 here. So this will be your 9 minus 1.4. So 9 minus 1.4 will give you 7.6. So your x2 will be 2. So your x2 is 2. Now again use the back substitution. Put the value of x1 and x2 here in the first equation. So we have 5x1 plus 2 plus 3 equal to 20. So your x1 is your 20 minus 5. So this is your 15 upon 5. So we have x1 equal to 3. Now please note that here we have interchanged our column 1 and column 3. Here we have changed our column 1 and column 3. So as we have changed our column 1 and 3, so we will interchange our variable x1 and x3. So our solution is given by interchanging x1 and x3. So therefore your x1 will be 1, your x2 will be 2, your x3 will be 3. Now you can verify this solution. Now just put the value of x1 here. So this is your 2, then we will have 8, then we will have 3. So your 8 plus 2, that is 10 plus 3 will be 13. Now put the value of x1 1, so this is your 1 plus 4, so this is your 5 plus this is your 9, so we have 14. So you can see that now these modified variables will satisfy our system of equation. So our required solution is equal to 1, 2, 3. So this is the solution with the help of the full pivoting. Now why this full pivoting is necessary? Let us solve a question and we will see that while partial pivoting gives you a wrong solution, but complete pivoting gives the solution. So again let us solve the question. Solve the problem 2x1 plus 2c x2 equal to 2c. Then we have the problem x1 plus x2 equal to 2, where your c is large. Now solve this again using the Gauss elimination method. So let us apply the partial pivoting. Here we will use the partial pivoting. Now you can see that your augmented matrix is equal to 2, then we have 2c, 1, 1, then we have 2c and 2. As we are using the partial pivoting, so in this column our numerically largest value is this 2. With the help of this 2, we will try to make this element 0. So we will use the operation R2 minus 1 by c, 1 by 2c of R1. So R2 minus 1 by 2c, 1 by 2 of R1 will give you. So you can see that this is your 2, then we have 2c, then here we have 2c. Now this is your 1 minus this 1 will be 0. So here we will have 1. Now this will be your minus c. Here we will have 2 minus this c. So this is your 2 minus c. So again, as our c is very large, so as our c is very large, So we can write it as, if your C is sufficiently large, then 1 minus C is same as your minus C. So in that case, as C is very large, so you can see that this is equivalent to 2C, then we have again 2C. Now this is your 0, then this will be minus C, and again 2 minus C will be minus C. So your solution is given by this equation, and we have 2C 0 minus C into the variables x1, x2, then in the right hand side we have 2C minus C. So from here you can see that your x2 is 1, and we have the equation 2x1 plus 2C x2 equal to 2C. Now if you put the value of x2 equal to 1, then you can see that your x1 equal to 0. So now you can see that x1 is 0, x2 is 1. Now let us check whether this solution is correct or not. So just put the value of x1 and x2 here. So if you put x1 equal to 0, x2 equal to 1, then the left hand side is 2c and we have the right hand side as 2c. Okay, this is correct. Now just put x1 equal to 0 and x2 equal to 1, then you can see that we have equation 1 equal to 2. So that means partial pivoting is giving the wrong solution. Again, if you not apply this pivoting, then again we will have the, without pivoting, we will have the solution as x1 equal to 0 and x2 equal to 1. So let us apply the full pivoting. So solution by full pivoting. Now, so let us apply the full pivoting. Now, in case of full pivoting, we have this sum matrix A. Now, here you consider as our C is greater than 1, as our C is numerically largest. So, you can see that this 2C is the largest element in this sum matrix. So, in case of full pivoting, our augmented matrices is equal to 2C, then we have 1, 1, then we have 2C and 2. Now here you can see that in this sum matrix A, our 2C is maximum value. So this is your numerically largest value, as our C is greater than 1 because it is very large. So let us interchange this column C2 and C1. So after interchanging this column C1 and C2, we have 2C 1, 2, 1, then 2C 2. So here we have interchanged our column C1 and C2. Now this is your numerically largest value. Now with the help of this element, again use the pivoting. So now here we will reduce this element 1 to 0. So we will use the operation R2 minus 1 by 2C of R1. So you can see that this is your 2C, then we have 2, then again this is your 2C. Now this 1 minus 1 will become 0. Now here we have 1 minus 1 by C, and here we will have 2 minus 1. So this is your 1. So we have 1 by C. Now as your C is very large, so this is equivalent to 1. So as our C is again very large, so this is equivalent to 2C, 2, again we have 2C, now 0, now as C is very large, so this will be a 1, and here we have 1. So solution is given by Ax equal to B. So we have 2C, 2, 0, 1, x1, x2 equal to 2C, then we have 1. So this can be written as 2C x1, 2x2 equal to 2C, then we have x2 equal to 1. So your x2 is 1, so just put the value of x2 here. So your 2C x1 plus 2 equal to 2c. So your x1 will be equal to, so your x1 will be, just divide this whole equation by 2. So this will be your c minus 1 upon c, and we can write it as 1 minus 1 upon c. Again, as our c was very large, so this is equal to 1. So your x1 is 1 and your x2 is 1. Now if you put the values in this system of equation, then you can see that this is your 2 plus 2c, and as your c is very large, so this 2c plus 2 will be equal to 2c, and this is your 1 plus 1, so we have 2. So when your c is very large, then the solution of this system of linear equation is equal to x1 equal to 1 and x2 equal to 1.